For over a century, space and time have been the stage on which physics unfolds. Objects move through space. Events happen in time. Gravity bends space-time. That was Einstein's revolution. But now, physics is asking something far more radical. What if space-time is not fundamental? What if it is not the stage, but a consequence? General relativity describes gravity as curvature of space-time. Massive objects distort the geometry around them. Planets orbit because space-time bends. The equations are elegant, and they work. Gravitational waves have been detected. Black holes have been imaged. Time dilation is measured daily in GPS satellites. Einstein survives, but when gravity meets quantum mechanics, something breaks. Quantum mechanics describes reality in terms of probabilities and fields. It works extraordinarily well at microscopic scales. General relativity works at cosmic scales, but the two frameworks are incompatible. When physicists attempt to quantize gravity, to treat space-time itself as a quantum object, infinities appear. Calculations lose meaning. The mathematics collapses. This is not a minor inconsistency. It suggests that our description of space-time may be incomplete. Recent theoretical developments suggest something extraordinary. In certain approaches to quantum gravity, space-time may emerge from something deeper, from quantum entanglement itself. In 2013, research in holographic duality revealed a striking relationship. The geometry of space-time in certain models appears mathematically linked to patterns of quantum entanglement. Remove entanglement, and space-time geometry collapses. Increase entanglement, and geometry stabilizes. This suggests that connectivity, not distance, may be fundamental. Space might not be a container. It might be a network. Some physicists propose that space-time is like temperature, real, measurable, but emergent from microscopic degrees of freedom. Temperature does not exist at the level of a single molecule. It emerges from collective motion. Space-time might be similar, emerging from deeper quantum information structure. If this is true, then asking where something is may not be fundamental. Location may arise from relationships. Meanwhile, experimental hints push us further. At extremely small scales, near the Planck length, classical geometry may break down entirely. Space-time could become granular, fluctuating, discrete. Some models predict space-time foam, microscopic fluctuations, where geometry itself becomes uncertain. We cannot directly probe the Planck scale yet. It is far beyond current experimental energy levels. But indirect effects may accumulate. Physicists are searching for tiny violations of Lorentz invariance, the principle that the laws of physics are the same for all observers. moving at constant velocity. So far, Lorentz symmetry holds remarkably well, but the search continues. Black holes also challenge our understanding of space-time. The information paradox forces a question. If information cannot be destroyed, how does it escape a black hole that evaporates via Hawking radiation? Recent theoretical work using quantum extremal surfaces suggests that information may be encoded in subtle correlations in radiation. Again, geometry and entanglement appear intertwined. The boundary between space-time and quantum information is blurring. Even time itself is under scrutiny. In certain quantum gravity equations, time disappears. The Wheeler-DeWitt equation, for example, does not contain time explicitly. It describes a static universal wave function. Time, in this view, may emerge from change within subsystems. If true, then the flow of time is not fundamental, it is relational. All of this suggests something extraordinary. The fabric of reality may not be fabric at all. It may be structure arising from deeper consistency. Physics is not destroying space-time. It is questioning its foundation. The history of physics shows a pattern. Newton believed space and time were absolute. Einstein showed they were relative. Now, physics may show they are emergent. Each step removes certainty from what once seemed fundamental, and yet predictions improved. Black holes merge exactly as equations predict. Gravitational waves match theoretical waveforms. Quantum experiments confirm non-local correlations. The world is not falling apart, but our conceptual foundation is shifting. We are moving from thinking of reality as built from objects in space to thinking of reality as built from relationships that generate space. This is subtle. It does not change your daily life, but it may change how we understand the universe at its deepest level. If space-time is emergent, then gravity may not be a force in the traditional sense. It may be a statistical effect of microscopic degrees of freedom. Some researchers even compare gravity to thermodynamics arising from entropy gradients rather than fundamental interaction. The implications are enormous. If space-time is emergent, then unifying gravity and quantum mechanics requires understanding the deeper layer from which both arise. We may not need to quantize gravity. We may need to rethink what gravity is. Physics is not at the end of discovery. It may be approaching its most radical transformation since relativity. The stage itself is under investigation. And if the stage is emergent, then the universe is more relational than we ever imagined. Still, within,